Hey, morning, everyone. Um, thanks, Chris, for the intro. I just want to echo what Chris said. Google has been collaborating really well with the open source community on numerous initiatives. In open source space, and also on the infrastructure side. Here, me and my team at Google very recently we started to take on the task of working on the space of Apache Hive and Hive Metastore. So really, this talk is about various things optimizations we recognize that exist in Hive Metastore and see how possibly we can take Hive Metastore to the next level. So this is a collaboration work with a bunch of my colleagues at Google, Chris, Cameron, Yunus, Zoe, and Yanbin. We have also been in fairly close touch with folks in Cloudera and also got a lot of help from them. So we also want to call like Tejas and Weihan for their help. Before I start into sort of deep dive into the content, I also want to give folks a brief history of Apache Hive and Hive Metastore. So really, the Hive project, I think, was originated from Facebook, and then I think in 2008. And then in 2010, I think they formally published the Hive paper in ICDE. And then around the year of 2013 and 2014, it became a top-level Apache Hive project. And now, at that time was tons of optimizations like arc support, vectorized execution, and so on and so forth. And then a few years after, people realizing the importance of Metastore, and they essentially try to push Metastore as a standalone module in the Hive repo. I think the first PR was probably sent out in the year of 2017. And then very recently, I think, recognizing the need for providing transactional rates. In the recent years, I think the Hive community has been focusing on introducing ACID capabilities on Hive managed tables. Very specifically in this talk and also in my team, we're very interested in, really make Hive Metastore work for all possible scenarios. So if you look at the open source ecosystem today, Hive Metastore, perhaps because it's maybe one of the first in the field, becomes the de facto standard for serving metadata and also for achieving a wider array of interoperability. So on this diagram, perhaps you realize Hive really sort of like sits on top of a number of different storage backends. There's HDFS, a bunch of cloud storage or cloud object file systems like GCS and S3. And there's also like some alternative, like newer formats, interesting formats, like Kafka, Elastic, and MongoDB. And then on top of that, pretty much all the major engines, they do support reading metadata from Hive Metastore. Things like obviously Hive Presto Spark, and also Impala and Hoodie. And then there's have also been a lot of like interoperability built between Hive Metastore and a similar, metadata management system, or in certain cases, access control. There's Atlas plugin, Ranger plugin, and also like Kerberos for providing authentication. Even some of the newer table formats, like things like Data and Iceberg. Even though they all started by perhaps recognizing there are inadequacies in Hive Metastore's metadata model, but at some point, I think both table formats, as of now, they all support a native integration with Hive Metastore as a catalog. So this is really like this whole slide really motivates us to spend the time and effort to really make Hive Metastore work for all possible cases. While behind the scene is actually not very hard. If you look at Hive Metastore architecture, it's actually fairly straightforward. It follows a very sort of standard two-layer approach. You have a computer layer, which takes the incoming request, do some processing, and write the data in a RDMS backend. So there you have a whole bunch of clients that talk to the Metastore through the Swift interface, and behind the scene, the data gets saved in a RDBMS. Can be MySQL, can be Postgres. So not really, too much, fancy, or it's not running a large sort of distributed setup and so on and so forth. So fairly straightforward. with that, the simplicity is great, but then we have also been seeing a lot of challenges with that kind of a setup. We have we have identified like a few ones that are perhaps important. So around interface scalability, and also sort of try to cope with ecosystem shift, which I will elaborate in the next slide. So the first one, which we recognize, like as of today, Swift, Hive Metastore is still using perhaps a decade-old interface protocol that's like RPC framework that's known as Swift. Is directly built on top of TCP. So that's why, in certain cases, it's really hard to be able to get like, annotations on per connection basis, or rather, be able to derive interesting metrics from a connection basis. Because again, you just see a pipe there, a TCP pipe there. So that's why the team's first effort to recognize that, perhaps we should modernize the interface to move towards more like a gRPC based, which is today widely, again, related to that, I think gRPC is also one of the OSS project originated from some Google's initial effort on protobuf on our internal stubby interface. So it gives us the benefit, like, for example, bypass payload size limit. And possibly, especially when you have like large partition data that you need to return through the wire interface, with gRPC streaming support, you might be able to reduce latency, and you can start serving immediately while waiting for newer metadata to arrive. And lastly, I know very recently, I think I've also saying that there will perhaps be a Hive meetup at some point. People have also talking about, how would you deploy an entire Hive in a Kubernetes environment. So obviously with gRPC, that makes your Hive Metastore easily integrated into the service mesh setup. So this is what I mean earlier, that with gRPC, really you can derive all this like per method metrics. You can have logs, you have monitoring metrics on each method, like what's the QPS for get table or get partition, and there you could also apply per method access control, so on and so forth. The second thing we recognize is, again, given that, Hive Metastore is primarily backed by a RDMS backend. And as of today, we have heard a lot of scalability concerns around that, being, it's hard to scale when you have really, really large amount of metadata. So recognizing that, we've also been trying to see, how can we make Hive Metastore work really on some of the latest horizontally scalable RDMS efforts. For example, in this case, we really look into ways to run Hive Metastore on top of Cloud Spanner. And it also helps to eliminate a single point of failure. So again, servers can be added and removed at will. Last thing is, again, how do we address some of the, ecosystem paradigm shift? People in these days have been talking about, the need of being able to support transactional workloads, things like time travel reads. So again, instead of us doing a very sort of patchy approach to say, hey, how can I just incrementally make Hive Metastore to catch up with a newer table formats? So here we're thinking about, are there ways for us to make sure, the Hive Metastore remains forward compatible with all these newer table formats? Again, we'll share some of our initial thoughts and early exploration in this space. So for each one, I want to give people a little bit technical details about how it's been done, and also like where's the project status and how you could possibly contribute. So on the gRPC, to roll out the gRPC support in Hive Metastore, the team took a two-phase approach. So phase one, again, for backwards compatibility, and also for, we aim to have it as a drop-in replacement. So therefore, we sort of try to develop a proxy. So really, this is the proxy that does protocol translation. Given, as I mentioned earlier, like Thrift is one way of doing remote, method calls, and then gRPC is another way. So ideally, and both aim to, have all this sort of properties from remote procedure call framework, take an interface, compile down those into, stubs and proxies that you can use locally, link your client application with. So recognizing that, we realize that actually it's not too hard to build a proxy to do, Thrift to gRPC conversion. So I just want to, perhaps I'll spend a few minutes just for people who want to know a little bit more about the technical details. So our approach is that, on the Swift side, we, based on that, existing Hive Metastore Thrift interface, we come and define the equivalent gRPC interface for that. So I gave an example about a get database request. It has strings and a list. Very similarly, we have the equivalent gRPC definition for that. And then after that, now we have the two interface files. Then we do the compilation using, Swift and gRPC compilers. So that would give us a standard set of, all these different classes. For example, you may have like a Swift generated get database request class. And similarly, you get, a proto generated get database request. And then we leverage this library again called map struct. So that map struct would allow us to easily write annotation-based mapper class. So you can say, hey, this is the rules of mapping this class to the other class. There are variations where it's hard to just use simple annotation. So we try to have like a common mapper class as much as we can. And in certain cases, we'll create a specialized mapper class to do the translation. So once we have the translation, it makes it really easy for us to implement this bidirectional proxy. So the proxy can be configured in both directions. So on the top, this is the direction from gRPC to Swift. Imagine that you have an incoming gRPC request. So the proxy will translate that gRPC using the mapper class approach I just described, turn that into a Swift class, and then forward that to a server that understands Swift. And conversely, on the reverse, on the pass from the server, then we're taking a Swift request and then translate that back to a gRPC. And the bottom is just like, it's a mirror image of the above. So we're foreseeing that, if at some point you realize, hey, I need to put my Hive Metastore in a service mesh, and I want to use, gRPC as the interface. So this is where you can conveniently package this proxy together with your Hive Metastore application. And there, you will be able to expose a native gRPC interface. And also, you don't have to really worry about modifying your existing client, because you would be able to have your client talk to another client-side proxy that translates Swift into gRPC. So this is the way, in the initial phase, how we can sort of provide this bidirectional compatibility. We have also been collaborating with the community and also try to come up with a design to really provide a native gRPC integration in Hive Metastore. So this is really like perhaps a 10,000 view sketch of how it would work. So essentially, we'll expand the Hive Metastore so that it can listen to both a Swift port as well as a gRPC port. So depending on the incoming request, then it will branch out either to the native, or rather to the existing Hive Metastore Swift server, or it's going to branch to the gRPC server. Incrementally, internally, we perform the translation, so you don't have to worry about proxy setup. But in the future, we do expect, there might be a direct link from the Metastore gRPC server to the backend object store. Like in this case, can be say MySQL. So this we have just sent. I think we have just submitted the first few PRs to the Hive repo. So if anyone is interested in trying out or learning out more about this, I'm happy to connect. Happy to talk to you and see how we can work together on that. The next one is really talking about, how do we build, HMS and call spanner to solve the scalability problem for Hive Metastore. As of today, going back a few slides, here we talk about, this is just a simple, direct link from the Metastore to the backend database. In fact, again, a lot of that simple connection, in fact, is expanded somewhat like this. So the way how the database is used in the Hive Metastore in-memory computer service is in the form of a JDO model, Java. You natively import those databases as Java classes, and then that is done through a data nucleus. For folks who are not quite familiar with data nucleus, it's essentially a JDO adapter layer, so that it could encapsulate all the details of connecting different database backends. So we take on that and then realize, what's the best way to be able to run Hive Metastore on Cloud Spanner. We have tried both approaches of, say, for example, have the Metastore talking directly to the Spanner database, but then realize that, that makes it really hard for us to be able to support all Hive Metastore methods. So instead, we opting for the data nucleus approach. Leveraging the latest JDBC driver for Cloud Spanner and extending the RDBMS adapter interface in data nucleus, we are able to, in fact, make sure the Cloud Spanner is now supported as a viable backend for data nucleus. As I mentioned, Hive recently introduced this Hive AC tables, which bypass. As you can notice, there's a direct link from the AC logic to the backend database. So we also spend the needed time and effort to make sure that path works as well, which there's a lot of tricky issues we have solved there, which I will elaborate next. So I'm going to stop and give a quick demo on this. Again, it will be, given the time limit, it will be a bit naive or toy-ish, but I guarantee you I'll show you some performance tests that we've done. So here's what I'm going to do. In my this is a Spark cluster. So I'm just running some simple Spark SQL command. So what I'm going to do, two things. I'll create a database, and I'll create a table in that database. Again, we'll basically, with that too, we inspect that the corresponding content or like metadata has indeed been saved in the Cloud Spanner backend. So I'll just say, let me try to zoom in a little bit. So I'll just say create database, Feng Lu, let's say meetup. And after that, I'll create a table inside this meetup. I'll say this is a great meetup so far. I'll give a name, and then I'll give a int. Just swap the order. Cool. So I have a database created, and then I also have a table created under that database. So here's what I'm going to do. So this is a great meetup. I'll go to the Spanner console, and then this is the backend Spanner sort of instance, and then we have all the tables. For people who are familiar with the Hive Metastore, maybe you can recognize tables like columns, databases, and also like tables. So I'll go to the database and just see whether I could find a table that corresponding to the meetup table we just created. So let me zoom in a little bit. As you notice, now we have this Feng Lu meetup table. And similarly, we go back to here and then just check that in my tables, I do have a table name that with great meetup exist. So again, I'll do a query, and then we go. Yeah, that's just to verify that indeed that data has been. So yes, so notice that this is the owner of the entry, and then again, you have the idea about the table name, and then this is being a Hive managed table. I'm happy to sort of share more in the demo, but given the time, I'm probably going to stop here for the demo, and I'll move on to the rest of the talk. So some of the technical challenges we faced, there's a 20K mutation limit in Cloud Spanner. Mutations define a row or column change. So that's why it's hard for us to ingest like a 20, when a table, when we want to make a, say load like 2000 plus partitions at once in a single transaction. So the solution we implement is really sort of partition that load automatically so that it will be done in parallel transactions. There's also some issue with cascaded deletion support. So that's why we have to change some partition and its subtables into interleaved. On the SQL and the gRPC side, there's also some quirks. For example, the driver itself doesn't really support nested query well. Whenever you have more than 1,000 nesting, Cloud Spanner is going to throw an error. So with that, we rely on some query optimization. And initially we wrote this very hacky solution by just replace the nesting with a in statement, so that make it work. The last one is for supporting some of the Hive ASIC tables. Because there's no sort of the lack of a select for update feature in Cloud Spanner, we ended up rewrite the transaction ID logic and switch to use Cloud Spanner's unique timestamp as a monotonic increasing sequence. As I mentioned earlier, this is not really a toy project. We did some setup, so we run a TBCDS 100 query benchmark, and then with 100+ clients. We do a comparison with MySQL, assuming that MySQL has sufficient capacity. So you look at the mean and 90 percentile latency. I think Cloud Spanner is a bit worse. At this point, for example, a mean latency, we're about like 43% slower. I just want to mention that we haven't had the chance to further optimize the setup. We do have some ideas about how this can be further optimized, but even without aggressive optimization, we'll still be able to see, is actually, in fact, the two performance are, in fact, very close to each other. And frankly speaking, with more, especially when you start to scale your SQL deployment, at some point, I think this is where the Cloud Spanner being a horizontally scaled database will win, and in terms of the performance. The project status right now, we're sort of trying to clean our code. And then over the next couple of quarters, we'll start to add the adapter code into data nucleus, as well as adding the code to Hive Metastore. So again, if anyone is interested in learning more about that, feel free to reach out to me. We can always work together to see how we can, for example, jointly optimize the performance. And maybe there are some other corner cases that we haven't really fully covered. The last thing I want to mention is this new idea that we very recently start to explore, see what is possible to provide auto-version of metadata. Again, that is inspired by the fact that Cloud Spanner provides native timestamp support. So it gives us a good sort of leverage to start to implement auto-version or time-based read on those metadata. A little bit of history, sort of, the challenge we try to address is really to how can we handle all this like a table format evolution. Hive Metastore organized table partitions of directories and subdirectories of files. That has been pretty successful. Very simple model, easy to understand. But there are also, at the same time, a lot of challenges with this data model. For example, the partition key. Whatever key you choose, that must be turned into a string, right? So if you have a null value, it's really all this like a weird one-off translation between a partition that's not a natural string column. So that's why recent table formats like Iceberg and Data start to depart from this table partitions directories directly and start to rely on explicit indexing in the table metadata. So the question is like, how could we native support those newer, and future table formats in Hive Metastore? So a couple of things we realize. A is, how do you really provide a convenient way for people to ask the question, hey, can you show me my metadata at this timing point? So it's one thing we realized perhaps we need to support. Second thing is really give this sort of a flexible metadata model. So far, I think the Hive Metastore schema or its metadata objects primarily designed around the notion where directories, tables are as directories. And partitions are subdirectories. So how can we sort of, perhaps provide a more flexible model so that, you could have partition, in fact, mapped to an arbitrary set of files, explicitly managed by the indexing. Alternative, the other thing we're also been thinking about is how can we better support these new table formats? Imagine now we have the opportunity to sort of involve the Hive Metastore metadata object model. So is that a better way? What things you can push down to the Hive Metastore? So very concretely, the thing we have explored so far is really to provide time travel read for Iceberg tables. So Iceberg, for folks who are not super familiar with that, it basically tries to store data and metadata alongside in a storage backend, say HDFS or S3 or GCS. And then you also write the table manifest data if you choose to use Hive Metastore as the catalog solution. And there it tells you the pointers to the Metastore file. So very, it's very easy for us to extend, let's say at the point when we have version metadata, because you can say, hey, at T0, your top level directories or your metadata file actually means file 1 and file 2. At time T2, your table metadata is 2 and 3. And now if I have a data engine that I want to query for, reading some Iceberg tables, I can give a timestamp. I can just read and then understand, oh, yeah, at this particular time, in fact, I should check those particular manifest files. So architecturally, this would look like the following. So on the Metastore service, we start to auto-version all the table changes. So in this case, if you have a full table, then you'd have like a V1, V2, V3, automatically version based on commit timestamp. So this is one feature we leverage again from our work on Cloud Spanner. So this really facilitates that anyone you can query, say, hey, give me the metadata or the table metadata at this particular timestamp. On the other hand, we'll have these new engines like Iceberg and Data start to again we make it appears more or less like transparent to the way how they interact with Hive Metastore today. But behind the scene, we take the complexity of auto versioning all the data and they push to the Metastore service. So this is a sort of a summary of what I just mentioned. Really start to auto version metadata in HMS, and then expand the current HMS Swift interface or gRPC interface to support timestamp-based query. It's like, yes, it's the same query as if you would otherwise say, give me partition data. But instead, now you can optionally supply, give me partition data at this time. And then initially at table level, just to bring time travel reads to Hive compatible engines. So as long as you have the Hive storage handler for a particular, for example, Iceberg has this external storage handler for reading Iceberg tables. And then with that, with this auto version table, then every time if you do provide a timestamp, we give you a previous snapshot of where those metadata file lives, so that you can get a sense, you can read at a particular time, even for like a non-Iceberg native readers. Again, this is really, really early in its initial stage. We'll be happy to hear all your thoughts, comments, telling us that maybe this is not the right approach and so on and so forth.